Okay, before I elaborate on this idea, I just want to refer back to a video that I told all grade 10 students to watch. It was the grade 9 algebraic expressions playlist. And in this playlist, I talked about the 3 different types of mathematical statements that we get. And one of the 3 was inequalities, right? So it's very important that you remember what that is, because in this video, I talked about the fact that with inequalities, there are a range of values that can make that inequality true. So it's a mathematical statement. In order for us to make this mathematical statement true, there are a range of values. But we could similarly say that there are a set of values that could make the mathematical statement true, or this inequality true. And the fact that I brought that word up, set, implies that we need to understand what a set is. And sets is by far one of the most misunderstood concepts, and it lends itself to many other sections. I can talk about this at length, right? It lends itself to number patterns, it lends itself to probability, it lends itself to functions, and many other sections in maths. So having a deep understanding of this topic will be very important. Now, it's a very simple section, but I just want to ensure that your knowledge is complete. Right, so let's look at the 3 properties of a set. So these 3 properties basically tell us what sets can be. Right, okay, so the distinct objects are called elements. So all of these things that are within the set are called elements. Like if you look at the natural number set, we have 1, 2, 3, 4, 5, 6, 7, 8, all the way up to positive infinity. Those numbers 1, 2, 3, 4, 5, and all the way up to positive infinity are called elements, right? Why do we say distinct? When we say distinct, we mean that each element must be different. So we cannot repeat an element. Very important. Say we have the numbers 1, 1, 2, 3, 4, 5, 10, 10. If I had to place these numbers in the set, I would write A. So what is this A? A is the name of the set. We'll say A is equal to, we make use of braces. This is what we call braces, right? And then when you're listing the elements out, you do not repeat. So the 1 is repeated here in this list, but when you put it into a set, you only can write 1 once. When you look at this 10 here in this list, it's repeated, but when you put it into a set, you cannot repeat. So therefore, we ignore any repetition. Right? Property number 2, we have either finite or infinite sets. Often in the case of infinite sets, we'll be asked to find an equation that will be able to generate any term in the set. So what are some of the examples of infinite sets? Natural numbers, whole numbers, integers. All of the numbers in the number systems are example of infinite sets. When we go into number systems, that's the reason why I said you will find an equation to generate any term in that set, because it's infinite. There's many possibilities that could make that mathematical statement true. So that's the reason why we have finite and infinite. So see here, this is an example of a finite set, because you have a full stop. It doesn't go on and on and on. But when you look at an infinite set, it goes on. We'll have ellipses, right? The 3 dots, and it'll go on forever. Right, property number 3, sets are enclosed within braces and are separated by a comma. However, in sets, order does not matter. Very important when we get into number patterns. The set 149 is the same as the set 491, and it's the same as the set 941. So whatever combination of you could get from this here, however you may change the order of these numbers, it does not matter. It'll be the same. However, this is not true for sequences, since order matters, and changing an element in the set may distort the pattern of the order. Yeah, so basically I discussed this module, the sets module, when I discussed number patterns at grade 10, but I'm just bringing it now because it lends itself to inequalities, right? So that's the reason why. You can take this down, but this is more pertinent for sequences. Okay, so there you can see I have an example. Here's a set. This is the name of the set. These are what we call the elements. These are the braces that we talked about, the comma, and yeah, elements, or we can call them members. Elements or members, same thing. An example of an infinite set, we'll put a comma and ellipsis here. An example of a finite set, we're saying that it ends, so we don't even have to put anything towards the end. We don't have to show continuation. Right. It's very important. I think there's a very big misconception. See this bracket here that we use all the time? It's called parentheses. This is what we call square brackets, and this is what we call braces. Right. So it's very important that you know the names of your different brackets. Well, it's not actually called. We generally say brackets, but it's actually called grouping symbols. So the correct thing to say is, it's important that you remember the different grouping symbols. So this is what we call parentheses, square brackets, and braces. Right? We often call this here brackets, but it's actually parentheses. Okay. Some rules to remember when naming a set: ensure that it is capitalized. You can see that I named the set with a capital letter. And if the set contains letters, then ensure that it is written in lowercase. The set of vowels represented by the letter V is A, E, I, O, U. You can see that all of the members of the elements of the set are written in lowercase, right? But this, we'll only work with numbers, but it's just some additional information for you. Okay, so now that we understand the basic idea of what a set is, and we understand some of the rules pertaining to sets, let's understand how do we represent them. Now, there are actually 4 ways that we can represent sets, right? But I'll show you the 3 now, and then when we're doing the inequalities, I will explain the 4th way. 3 common ways of denoting sets, namely roster notation, set builder notation, and interval notation. The 4th way here you can say is the number line, right? But it's not actually useful when we start talking about all of the other sections. That's why I don't mention it here. These are best explained using an example. Note, you may not necessarily be tested on writing with these notations, but it would form part of the foundation in maths when working with topics like domain and range, probability, and inequalities. Now, that's very important. The section you may not be marked directly for the section, but they may put this section in other sections like domain and range, probability, and inequalities. So understanding this will be very important. Let's consider the following example. List all of the whole numbers less than 8. So let's just think of this here, right? We have to list of all of the whole numbers less than 8. What are whole numbers? Whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, isn't it? So if we're listing the whole numbers that are less than 8, not 8, less than 8, it will be all of these numbers here. Would you agree? So how do we represent this using these different notations is what we are going to do now. Right. In this method, we simply list all distinct elements of the set. We must first understand the question fully. In this case, we see that it is stated that we must write the whole numbers, which we know to be a special infinite set. I've already talked about that in the number systems video. It's special because we give it a name under the number systems video, and it's infinite because it has no boundaries. It goes all the way up to positive infinity, and it has to be less than 8. So it has to be a whole number. It has to be whole numbers and less than 8, implying that we should not include 8. That's very important. Verbally, we say A equals the set consisting of numbers or elements 0 to 7. The way we would denote this is, A is equal to a brace, open brace, 0, 1, 2, 3, 4, 5, 6, 7, close the brace. And that's how you do roster notation. You list the elements, the distinct elements of the set. Now, sometimes for large numbers, we may represent it as follows: 0, 1, 2, 3, 4, ... comma 51. Now, what this does is, by listing a few numbers, you understand that there's a pattern. What's the pattern? Is that we adding 1 to every previous number. We are listing the whole numbers is basically what we're saying. But here we are ending with 51. So the first few numbers defines a pattern. It shows you what the pattern is. The dots here skip all of the other numbers, so we don't have to list this number 51 times. And the last number tells you what's the upper limit or the upper boundary where the numbers end. By listing a few numbers, we get to see a general pattern that the numbers in the set are whole numbers. This approach is not convenient for large numbers. Very important. So although it is useful in certain scenarios, it cannot be useful in every scenario. So therefore, we use something else called set builder notation, which is our second way of representing sets. So let's move over to that part. Okay, so the next way that we can represent sets is by set builder notation. Sounds fancy, but it's a very simple idea. In set builder notation, we do not explicitly write each element. However, we generalize, not forgetting to state any limits. In this case, less than 8. The E sign means element of, meaning that it is a member or object or element in or of the set that comes after the symbol. In this case, the set of whole numbers. So let's look at this here, right? Let's deconstruct it. A equals to a set of all x's such that x is an element of whole numbers and x is greater than or equal to 0 but less than 8. So basically what this means is we're giving the set a name, right? You put a bracket. Then we give it a variable, and the reason we use a variable is because we try to show what numbers this set contains, the set A contains. We use this by a means such that, and then we name, if let's say for example we're dealing with a special set, like natural numbers, whole numbers, integers, rational numbers, irrational numbers, or real numbers. We name what set in general these numbers come from. So in general, this x comes from whole numbers, because we told that it comes from whole numbers, right? Then if we leave it as it is here, then we're talking about every whole number. But we know that there's a restriction. What is the restriction? The restriction is that x lies between 0 and 8. Now watch here. Let's say that we did not put this part here. Right, let's say that we did not put that. So it'll be important that I explain this so that you understand why we put each part. Let's say I don't put this part here, and I just left it like this here. Then what does x greater than equal to 0 less than 8 would imply is that we could have 0, right? We could have 0.1, 0.2, 0.3, 0.4, 0.45. The point I'm trying to make here is that these numbers can go into decimals. But what did the question state? That it has to be whole numbers. So what we do is, by stating that these numbers have to be whole numbers, we eliminate all of these options, all of these decimals. Right? If I have to explain this using a number line, and if I have here 0, 1, 2, 3, 4, and so on, see, everything in between 0 and 1 will represent fractions. 0,1, 0,2, 0,3, all the way to 1. Everything in between 1 and 2 will represent fractions again. The decimals, 1.1, 1.2, 1.3, 1.25, 1.26, and so on. However, by stating that these numbers have to be whole numbers, instead of going to these values with the decimals, we're going to these discrete values, to these exact points. Understood? That's what we mean by discrete. It's at that point. It's exact. There's no decimals to it. Understood? So that's the reason why we have to state what set, if possible. If they said that the numbers are between must be greater than 0 but less than 8, and they didn't state that it must come from the set of whole numbers, then this will be applicable, because it implies that all of these decimals that come in between here, in between here, in between here, will satisfy that statement. Understood? But by stating this restriction now, we are eliminating all of their options and sticking to only that discrete value, that at that point, at 0, at 1, at 2. It cannot even be 2,0000001, which is just a fraction after 2. It cannot be that, because we are told that it has to be from the set of whole numbers. And see this word e, element. What did we say? What do we call the numbers in the sets? Elements. So when we're saying that x is an element of, means it's a member of these values x, right, that makes up the set A, comes from the whole number set. Understood? And there's the restrictions here. So yeah. So how do we structure it out? We say that A, we name the set first, then we choose x or any other variable y. We want to show the range of values that belong to the set A, right? So you just give it a variable because we want to show what are the different values that belong to the set A, right? Because now remember, we're not listing out explicitly. We're not stating what each or listing every possible number, right? And however, we use x for convenience, and it is a letter that we do not confuse it with another set. The bar means such that you can choose to also use colons. So it could be dot dot. You could do that, or you could use the bar. Both means the same thing, such that whatever follows the bar, so whatever follows the bar describes x, right? Or whatever arbitrary letter you use. Whatever letter you use. Let's say you used y. Whatever follows this bar describes what A is. It describes that A is coming from this special set, right? The nature of it. And then we describe what the limits are. The lower limit is what? That it must be greater than or equal to 0, and the upper limit, it must be less than 8. That's what we mean by limits. Well, oftentimes, you don't have to name the set always. So what you could do is just this part here. And this is also a part of set builder notation. So if you give it a question and you answered it just like this here, watch here. You answered it as x is an element of the natural number set, and x must be greater than equal to 0 but less than 8. Alternatively, you could say x is an element of the natural number set, but x must be greater than or equal to 0 but less than or equal to 7. Right? You can see both of this here means the exact same thing. Both of these notations. So naming the set here and saying x, giving an arbitrary letter, is not very, very important. What makes set builder notation is this greater than and equal to sign, what we call inequality signs. right? This is why we're going to use this here when we're talking about inequalities, because these are called inequalities because it's not an equal to, it's not an equality sign. It has the greater than, less than sign, or greater than or equal to, or less than or equal to. Right, so I just want to stress something again. Because our minds are so calibrated to only thinking about counting numbers like 1, 2, 3, 4, 5, 6, we forget that when we look at this number line, that in between there's numbers that are decimals. In between here, there's numbers that are decimals, and so on. So what tends to happen is that we forget to think about it. That's why we forget to state this type of set that these numbers belong to. Because if you state this here, what you're implying that all of these numbers make up the set, but that's not true. That's not true. Right? It's only these numbers at this point. These numbers at this point. Right? Remember, if you move slightly, even slightly to the right, you have a fraction. If you move slightly to the left, you have a fraction. Like this will be 3,999. Think about this. At this point here, it will be 3,9999 and recurring. Right? Getting you as close as possible to 4, but not 4. Here you'll have 4,000000001. Just a fraction away from 4. Well, that's the reason why, to expand your mind a bit, you have to state where these sets come from. So it's actually the whole number set, so you have to include the 0 at the bottom. You have to state where these sets come from, because if you don't, then you imply that we are dealing with fractions as well. And just because your mind is naturally thinking about the counting numbers, like the natural numbers 1, 2, 3, 4, 5, remember, there's decimals in between here, right? Okay, now let's talk about interval notation. We use brackets to denote sets in terms of interval notation. Right, let me repeat that. We use brackets to denote sets in terms of interval notation. So the correct word that we're supposed to use is grouping symbols. And which two types of grouping symbols we use? We use the parentheses or the square brackets. Understood? What do these mean? If you use parentheses, we imply that the number is not included in the set. So in other words, it is excluded from the collection of objects. It is very similar to the less than sign or the greater than sign. If we use square brackets, we imply that we're including the element in the set. So it is included in the collection of objects. This is very similar to the greater than or equal to sign and less than or equal to sign. Okay, so now let's first work with this, and thereafter I'll talk about all of the different ideas that we have here, right? So we said that we need to state all of the whole numbers less than 8. So how could we do that? The first thing is using this the interval notation. We can say A is the element of. So what is A? Is renaming the set. Is the element of. So whatever you have in the brackets represents all of the numbers that makes up that set. It's an element of the set. Right? Remember when we did standard sets, we used the braces. But when we use the braces, we have to state all of the distinct elements. And we said that it becomes inconvenient when you start working with bigger numbers. So what we do now is, when we with this idea here, with the interval notation, we make use of grouping symbols. If you use a square bracket, then you include whatever number that you have there. If you use a parentheses, then you're excluding the number that's stated. For example, what this means now is that A is an element of the set from 0 to 7, not 8, to 7, because it's not including it. See the square bracket, this parentheses implies that we are not including whatever number comes before it. But if I stated it just like this, it implies that we will take fractions like 0,00001, 1,1, like 2,5, because we were told that we must list the whole numbers less than 8. That's the reason why from all of that many different possibilities, we zoom down and refine it by stating this part, whole numbers, right? Because what the whole numbers do now is, it enables us to take out all of the fractions and only focus at that discrete point. The exact explanation that I did with set builder notation. Even here as well, see here we could have explained it alternatively using only square brackets, because we can include both extremes. So you're stating the two extremes, the lower and the upper. That's what you're doing with this notation. You're stating extremes here. This is the lower extreme, that's the upper extreme, right? With the lower extreme, are you including it? Yes, then use square brackets. In this case, the upper extreme, are you including it? Yes, then use square brackets, but then state what types of numbers these are, right? So it has to exist in the whole number set. In this case, both sets imply the same thing. We say A is an element of the set from 0 to 7, and set A consists of whole numbers. So A is an element of the set from 0 to 7, and A consists of all numbers. However, in the first case, we exclude the 8. We're excluding it. So the next whole number that is less than 8 has to be 7. See what I said there? I said, okay, if I didn't take this part here, if I didn't include that part there, right, I'm excluding 8. What's the next number close to 8? Will be 7,99999 and so on. Recurring. That's the next number that is as close as possible to 8. But the fact that I included that restriction, or the fact that I spoke about what the nature of these numbers have to be, then I must ask myself, what is the next nearest whole number to 8? But less than 8, because that's the upper extreme. It is 7. So 7 is the next nearest whole number less than 8. That's the reason why we're using the parentheses. When we use the parentheses, that's what we're excluding the upper boundary, but then you need to look for the next nearest whole number. So this is why this is true. This is what enables us to do that. Right, n7 is the last element of the set and not 8. In case 2, we included 7 and hence it is the last element of the set. Right, just one more thing to bring to your attention. Let's say we want to talk about infinity. Let's say that a set has infinity in it. Then you cannot use square brackets. Since infinity is not tangible, we haven't really got, no one has actually ever got to that actual point of infinity. We just say that it's far to the right, or negative infinity is far to the left. Hence we'll use the parenthesis. So let's say, that they tell us list the natural numbers. So I'll say, okay, A is an element starting from what number? 1, going to what number? Positive infinity, but you cannot use the square bracket, you have to use the parentheses. And A is an element of the natural numbers. So the point that I'm trying to make here is that whenever you use infinity, whenever infinity is involved, you cannot use a square bracket, you have to use a parenthesis. Right? Even if you have to do the whole numbers, then I'll say A is an element of the set starting from where? A 0 going to where? Positive infinity, close the bracket. A is an element of the whole numbers. Right. Then let's say we're talking about the integer set. I'll say A is an element starting from where? Negative infinity. You can see I use a parenthesis. Going to where? Positive infinity. But A is the element of integers with the Z. So it's the exact same idea. Can you see why it's all important now? Everything links. So yeah, so that's basically what you need to remember. Right, so again, when you're dealing with set builder notation, you're dealing with inequality signs. So the less than or equal to sign, the greater than or equal to sign, the less than sign, or the greater than sign. When you're dealing with interval notation, you're making use of grouping symbols. So like the parenthesis or the square brackets. Very important stuff. So you just need to know the distinctions. With the roster notation, we hardly ever use it because it's very inconvenient to work with larger numbers. So that's the reason why we stick to only this two. Now, understanding the difference between these two is very important, because sometimes you could be asked explicitly to use set builder notation, or you may be asked to use specifically the interval notation. So you need to know what to use when. And then the number line is the last technique that I will talk about when we're working with inequalities. So keep space here so that I can talk about number lines, because it's a very easy one that forms a part of linear inequalities.